Okay, what's going on, everybody? Today I'm going to talk a little bit about ground reaction forces captured during walking, and I'm going to go through vertical and anterior posterior ground reaction forces and create a MATLAB script that will pull out some variables that are very commonly reported when dealing with this kind of data. So the first thing I'm going to do is just load up some example ground reaction force curves that I kind of pulled from some data that I have earlier. I've stored them in this MATLAB structure called vars, and you'll see I've got 4 different speeds. So this is 0.8 meters per second, that's speed 1. 2 is 1.2 meters per second, speed 3 is 1.6 meters per second, and speed 4 is 2.0 meters per second. And you'll see when I go into these, each one of those speeds has the time series data for ground reaction forces from a force platform in all 3 dimensions. Today we're going to go through vertical and anterior posterior ground reaction forces. Just to show you what these look like across speed, I'm going to create a figure and plot from each speed. So from speed 1, I'm going to plot the ground reaction force in the vertical direction. And then I'll plot these for each speed just to get an idea of what we're going to be looking at. So change this to speed 2, this to speed 3, and this to speed 4. And then we'll make these different colors so we can tell them apart. So we'll make speed 2 red, this one will be magenta, and this one will be black. Okay, let's plot these. Okay, so what we're looking at are very typical or stereotypical vertical ground reaction forces captured during walking. They're very commonly this bimodal shape. And you can see that as you speed up, as you go from blue to red to magenta to black, the peaks on these get a little bit higher. They also get a little bit shorter. This means that the support time, or the time that the foot is generating forces onto the ground, is getting shorter. So one of the things that we'll calculate here is support time, how long the person stays on the foot. We'll also go ahead and calculate each of these 2 peaks and the area under the entire vertical ground reaction force curve. Now let me plot, instead of the vertical, let me plot our anterior posterior. With our lab setup, that's the Y direction. So let me plot these. And you can see the same thing, they get shorter. That support time is getting shorter. You can see here really clearly that as you speed up, these peaks, both peak braking or peak negative and peak positive, and or sometimes referred to as peak propulsion, these get way larger. The area under these curves, although they're getting shorter, they're increasing. And so what we're going to do is calculate from the anterior posterior these peaks. We're also going to calculate the area under the positive and the negative aspects of this. And then to make things a little bit more interesting too, we'll calculate the timing of these variables, the timing of these peaks, for example. I've started to think of a lot of these variables in the time domain rather than, or calculating timing related aspects of these rather than just magnitude related aspects of this kind of data. Okay, so what I'm first going to do is find out how many fields we have. So let me just do this. If we were to create a for loop that's going to go through each speed iteratively and calculate these on each of the curves, one of the things we could do is just create a for loop that goes 1 through 4. So we could say for I is equal to 1 through 4. That's because we know that we have 4 speeds. A way to make this a little bit more robust would be to actually automatically find how many fields we have. So we could say fields is equal to field names in bars. Let me just show you what field names gives us. If I were to run this right down on my command window here, you actually see it gives us a list of all of the different field names. So here we could just count the number of elements within fields, and that would give us 4. So that's exactly what I'm going to do. I'm going to say, instead of saying 1 through 4, I'm going to say num L, which is number of elements in fields. All right, so we're going to go 1 through the number of elements in fields, which should give us 4. Oh, not enough arguments. Num L fields. Oh, it helps if we run this first. So this should give us 4. Hey, there we go. All right, so let's give ourselves some room here. The first thing I want to do is just define my vertical and anterior posterior ground reaction forces. We're going to say GRFV is equal to vars dot. Now we need to vary which speed we're bringing in. So we need to iteratively vary the field name that comes in. So what we're going to do is we're going to call fields, and we're going to say I. So this is going to call, if I is equal to 1, this is going to call speed 1. If it's equal to 2, it's going to call speed 2. If it's equal to 3, it's going to call speed 3. And then 4, it's going to call 4. And then we want this to be the GRFZ. Okay. And then we want GRF AP to be equal to vars. Same thing. We have to iteratively change our field name. Okay, and then instead of GRFZ, we're calling in GRFY. Let's go ahead and make sure that that works all right. Let's just run these. We need to give I, so let's imagine that I is going to be equal to 1. And then let's run these. I'm just setting I equal to 1 for right now to make sure that these work. Okay, let's go ahead and, just to make sure, let's go ahead and plot one of these, GRFV. Okay, and it plots. So we're pulling in this data, all right. Okay, so let's see, what did we say we wanted to do? We want to get the support phase, length of the support, so support time. Okay, so for support time, it's going to be pretty simple. What we need is, we're going to call this support time, and we're going to just take the length of GRFV. Now this is length in frames, right? So what we really need is length in time, and so for that, what we'll do is we'll specify a sample frequency. So I collected data at 1,000 hertz, 1,000 frames per second. And so if we know that this is how many frames are there, we can just divide that by the sample frequency. And that should give us time in seconds. So let's go ahead and run these two things and see what that gives us. The support time for this particular step is 0.96 seconds. So this is support time in seconds. All right, now let's look into some of the actual ground reaction force variables. So let's start with vertical. Let's start with the vertical first and second peaks. So remember we had that bimodal shape. We want to get the first and second peaks. Well, as it turns out, MATLAB has this great function called find peaks. So we'll say the vert peaks are equal to find peaks, and then we can just pass in GRFV. And what this is going to do is find all of the peaks on that curve. And so we can call that, and then vert peaks you can see is 837 and 838. So the first peak is 837 and the second peak is 838. Now, suppose for a second we also want to know where those are. We want to know their indices. We can pass in vert peak indices, and then that would give us not only the peaks themselves, but also where they are, what frame number they're at, 335 and 687. Now, find peaks is just looking for things that go from a number that is lower to higher to lower again, and then it's going to give you that top number. So that's what this find peaks function, it's a built-in MATLAB function, is doing. You do want to double check this because it's possible that there's some little glitch in your data, or maybe it's not a glitch, it might be real data, and it's going to pick it up as a peak. And so one of the things that you can do is just plot these to make sure that they look right. So we'll plot GRFV, and on top of that, what we're going to do is plot these peaks. So we're going to plot on the x-axis, it's going to be the vert peak indices. And we're going to do the first peak. And then on the y-axis, it's going to be vert peaks. And we're going to do 1. And we're going to make this a red circle. And then we're also going to want to plot that second peak on top of there. So we'll just copy this and paste it. And we'll change this to 2. And this to 2. And we'll make this we'll do a green circle. we're going to call UI weight. This is so when I run this later, UI weight holds the rest of the code from running until I exit out of the current figure. So let's just plot this right now, make sure this looks okay. Okay, so look at that. So that's our first peak and our second peak. So this is identifying two peaks, and it's identifying them correctly. So what we'll do is we'll set vert peak 1 is equal to vert peaks 1, and then we'll set the second peak to vert peaks 2. Okay, simple as that. All right, so there's our peaks from our vertical. Now let's go ahead and get the vertical impulse. The vertical impulse, we're going to use the trapezoidal integration function here, and this is built into MATLAB, so we'll say vert impulse is equal to traps. Again, this is built in, and we're just going to pass in grfv, and this is going to give us the area relative to frames, but we need to pass in our sample frequency, make it relative to time. So let's make sure this runs. This is our vertical impulse, or the area under that vertical ground reaction force curve. So there's our impulse there. All right, so these are two things that are really commonly reported when you see vertical ground reaction forces during walking, those two peaks and the area under the curve. Sometimes people will split it into the first 50% and the second 50%, and they'll give you different areas for what half of the support phase you're in, but we're just going to do the whole impulse here. Okay, so we did support time, we have these vertical ones. Let's go into now the anterior posterior peaks. So let's get peak, negative, and positive from the AP graph. So you can probably imagine what I'm going to do here. This is relatively easy. We'll say AP peak negative, and this is going to be just equal to the minimum of the ground reaction force anterior posterior. Now let's also go ahead, because I'm going to calculate the timing of these peaks as well, let's go ahead and just get the index for this too. So AP peak negative index, and I'll show you why we're doing that in just a moment. Okay, so let's go ahead and copy this. So that's going to give us the minimum ground reaction force, minimum anterior posterior ground reaction force. Let's copy this and paste it, and then instead of negative, we're going to get the positive. So in our lab, negative values indicate posteriorly directed forces, and positive values indicate anteriorly directed forces. So instead of min here, which is going to give us that peak negative, max is going to give us the peak positive. Okay, so let's go ahead and run these, make sure these run. Let's go ahead and take a look at that peak negative, negative 74. Let's go ahead and take a look at this peak positive, positive 88. Okay. Now, let's see here. What else do we want? Oh, yes, we want positive and negative impulses from these. Let's go ahead and get those. So for the negative, what we're going to do, we're going to say AP braking or brake impulse. Let's call this negative impulse is going to be equal to, again, we're going to use that traps function. So this is built-in function in MATLAB. So AP negative impulse is traps, and we're going to call in grf AP, and then we're going to subset this. So grf AP, where grf AP is less than 0. And then we're going to do the same thing. We're going to divide this by our sample frequency. So let's go ahead and run that, make sure that runs. We got it, negative 22. Okay, I'm going to copy this. And instead of negative, we're going to go ahead and get the positive impulse. And instead of where the AP GRF is less than 0, we only want to subset it to greater than 0. And let's run this. It should be approximately equal to the negative impulse. This impulse across the entire step should be close to 0. So 18. So it's a little bit under the negative. But if you take a bunch of steps back to back to back, over a lot of steps, you typically get an average total impulse, which is positive and negative. You usually get that around 0. Okay, so the last thing I want to do with these is just calculate the timing of them. I like to think of these peaks as not just a magnitude, which is what's very commonly reported, but also I'm interested in the timing of them. And for this particular code, I'll show you how to do the timing relative to the support phase. So it's going to be a percentage of the support phase. Let's get timing of peak, negative, and positive values. And we'll call this AP peak negative time is going to be equal to, remember we have the index for it, but what we're going to do is take that index, this is the frame at which this peak occurs, and we're just going to divide it by the length of the entire thing, so GRF AP. And then to make it a percentage, we're going to take that ratio and we're going to just multiply it by 100. And this will give us the percentage at which this peak negative occurs. And so let's run that. You can see it occurs at approximately 27%, not approximately, it occurs at 27% of the support phase. And we're going to do the same thing with peak positive. So we'll copy that and paste it, change the names accordingly. So whereas this is negative, this will now be positive. And this, of course, should occur later in the support phase. So let's make sure that that checks out. Perfect, 85%. Okay, so these are the things that I want to calculate. The last thing I want to do is because we're doing this on every speed, what I want to do is compile all of the results. So I'm going to do that up here and say all speeds. I'm going to just initialize this as an empty matrix. And then down at the bottom, after I've calculated everything, I'm going to, for each loop, I'm going to take all these things I'm calculating and add them up into this, this variable here. And then at the end, outside of this loop, we can plot some things and see what they look like across speeds. So we're going to say, I'll copy this. We'll come down here within this for loop, give ourselves some space. So all speeds, so across all, on row I, so each speed will have its own row, across all columns, what we're going to do is add each of these variables. So the first one that we did was support time. And then we got the peak 1, peak 2 from vert and the impulse. So we got vert, peak 1, vert, peak 2, and vert, impulse. Okay, and then what did we get? We got the AP peak negative and AP peak positive. Okay, and then we got the negative and positive impulses. This is pause. And then we got the timing of the peaks. Change these accordingly. Okay, so this is 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10 variables related to these ground reaction force curves that we're calculating. We're calculating these across 4 different speeds. So let's go ahead and run this. Hopefully it all runs okay. Underneath each plot, I'm just going to throw a UI weight. Okay, I'm just making sure all this stuff looks good. I think it's good. Let's go ahead and run it. At the end, we're going to have all of these variables across all speeds, and then we'll plot a few of these across speeds to see what they look like. So let's clear this, do a clear all, clear the command window, and let's go ahead and run this. Okay, so remember we plot all of them. These are all the speeds. This is speed 1. This is just, I put this in here just to make sure that it's pulling the peaks correctly. So that one looks good. This is speed 2. That one looks good. This is speed 3. That one looks good. And this is speed 4. And that one looks good. And I'm just plotting these on every loop just to make sure that find peaks is doing what we want it to do. Okay, so you see it ran just fine, and now under here on all speed should be, a 4x10 double, so each row is a speed, and then each column are the variables. So you'll remember this is support time, this is vertical peak 1, vertical peak 2, vertical impulse, peak braking, peak propulsion, negative impulse, positive impulse, and then the timing. So let's go ahead. What we can do is we can come down outside of this for loop, and we can create a figure, and we can plot all speed. Let's just say, let's see if support time changes. We know that it does. All rows of that first column, and then what we can do is, so let's plot these as red circles. And then to make this look good, we're going to add art X ticks, and we're going to say 1 by 1 to the 4. Okay, you know what? Let's make this look a little bit better by filling these in. Be a little bit easier to see. Okay, so there you go. So this is speed 1, speed 2, speed 3, and speed 4. And that is, as you can see, as you speed up, as you walk faster, apologize if you can hear this, the sirens outside there. As you walk faster, support time decreases. And that's what we saw when we were looking at the ground reaction force curves. Okay, and then we can change this column, so we can, go to, let's say we want to know whether the peak propulsion, which is our column 6 here, changes across speeds. And yeah, you can see, so as you speed up, this peak goes way up. Okay, I hope you guys enjoyed that video. Just a quick session on ground reaction force curves during walking, some of the things that people typically pull out of them, how you can do it across different speeds, how these things change across speed. If you did like this video, go ahead and give it a thumbs up. Subscribe to my channel to see more of this. You can also find me on Twitter, of course here on YouTube. My academic work is on ResearchGate, and you can find a lot of my codes up on GitHub, and you can also find me on LinkedIn. All right, until next time, keep coding.